In the last few lectures, we were looking at different flow patterns in different geometries. We first looked at flow through a pipe, where there was a transition between a laminar and a turbulent flow at a Reynolds number of about 2100. Then we looked at the flow past a flat plate, where the projected area perpendicular to the flow is negligible. So, there is very little disturbance to the streamlines. However, the zero velocity condition at the surface implies that there is a shear stress exerted on the fluid. And there also we looked at the boundary layer thickness, within which there is a disturbance to the velocity field due to the plate surface, the laminar and the turbulent regimes, and the friction factor correlations. And then we looked at the flow around objects, spherical objects, particles with a no slip condition at the surface. Here the only parameter is the Reynolds number, which is based upon the free stream velocity, the relative velocity between the particle and the fluid far from the particle, okay, that is the free stream velocity. And we defined a Reynolds number based upon particle diameter and the free stream velocity, and identified regimes where we have laminar flow and for about Reynolds number less than about 1.5. The streamlines are symmetric between the upstream and the downstream sides. Between about 1.5 and 24, we get asymmetry in the streamlines because of inertial effects. Between about 24 and 400, there is a separation bubble on the rear side of the particle, within which there is complete recirculation, and that separation bubble is attached to the particle. Increase the Reynolds number further, you get a wake which is oscillating with periodic vortex shedding. Above about 4000, the wake becomes turbulent and the drag coefficient becomes close to a constant, and once at about 2 into 10 power 5 Reynolds number, you have the drag crisis, where the attachment points of the wake shift downstream and the boundary layer on the upstream side of the particle is also turbulent. And we had looked at drag coefficients in different regimes and shown how to calculate them. We had also looked at drag coefficients for the flow around a bubble. In this case, you do not have separation bubble formation, wake formation, etc., because of the difference in the boundary conditions. For the flow past a bubble, there is a zero shear stress condition at the surface, and therefore there is no resistance to flow at the interface. In contrast to a particle where you have a zero velocity condition at the surface, and there is resistance to flow at the surface. Therefore, in a bubble, the drag coefficient is proportional to 1 over the Reynolds number, both at high and low Reynolds numbers. At low Reynolds number, it was 16 by Re, and at high Reynolds number 48 by Re. For a particle at low Reynolds number, if it was 24 by Re as we expect, and at high Reynolds number it went to a constant value of about 0.4 until there was a drag crisis at a Reynolds number of 2 into 10 power 5. So, next we will look at momentum transfer in the flow through packed columns. Typically, you would consider a column which contains particles in it. There is usually a plate at the bottom which to hold the particles, and these particles have these particles of course rest on each other. So, I am just drawing it schematically. And these particles have characteristic diameter d, okay, dp. I will call this dp for the particles. Okay. And the bed will typically have a cross sectional area A and length L, and the total volume of the bed, volume of the column, is equal to V. Okay, that is the total volume of the entire column. And it is filled with particles of diameter d, okay, particles diameter dp. Okay. This will have volume Vp and surface area Ep. Okay. If it is an irregular particle, you should use the equivalent diameter instead of the diameter itself. Okay. If the particle is irregular, you should use the equivalent diameter instead of the diameter itself. Recall that the equivalent diameter is defined as d equivalent is equal to Vp by 6, I am sorry, 6 Vp by Ep. That is the equivalent diameter, 6 times the volume divided by the surface area. For a spherical particle, volume is pi d cubed by 6, surface area is pi d square. So, the diameter, equivalent diameter is equal to the actual diameter of the particle. Okay. And then there is something called the void fraction. Epsilon, okay, which is equal to the 1 minus volume of particles by total volume. Okay. This is actually the free space in between the particles, the volume of the free space in between the particles to the total volume, the ratio of the volume of the free space between particles, that is total volume minus volume of particles divided by total volume. What fraction of the total volume is available for the fluid to flow through? Okay. That is called the void fraction. Okay. So, the fraction of volume occupied by the particles is 1 minus epsilon. Okay. So, this is the parameter that is used, and there is fluid flowing through this. Okay. There is fluid flowing through this. So, this is described by a superficial velocity Vs. Okay. Vs, superficial velocity, labeled as superficial velocity because this is the velocity with which the fluid will flow in the clear space if there were no particles. Okay. So, in the bed without particles, the fluid will flow with the superficial velocity Vs. Okay. Once it goes through the voids between the particles, the velocity has to increase because the cross sectional area has decreased. Okay. So, therefore, the velocity through voids will be ratio of the superficial velocity and the void fraction, because the area available for the fluid to flow is equal to the void fraction times the total area of the column, okay, the total cross sectional area of the column. Not all of it is available for particles to flow because there is, I am sorry, not all of it is available for fluid to flow because a fraction is occupied by the particles. So, the velocity through the voids is equal to the superficial velocity divided by this void fraction. Okay. Okay. So, there is fluid that is flowing only through the voids, okay, and the velocity through the voids is the superficial velocity defined. If there were no particles, what would be the velocity? The flow rate divided by the cross sectional area of the bed without particles. The flow rate divided by the cross sectional area of the bed without particles is the superficial velocity, and the velocity through the voids is Vs divided by epsilon. Okay. Now, since the fluid is flowing through the voids between the particles, the characteristic length scale that has to be used for this flow is the equivalent diameter of the voids. Okay. The equivalent diameter of the voids is the characteristic length relevant for this particular flow. Okay. What is the equivalent diameter of the voids? Okay. The equivalent diameter of the voids is equal to 6 times volume of the voids by surface area of the void. 6 times the volume of the voids divided by surface area of the voids. Okay. The volume of the voids is just equal to the total volume times epsilon, the void fraction. That is the volume of the voids. Okay. The total void fraction times epsilon is the volume, void volume available for the particles to flow through. What is the surface area of the voids? Okay. Now, the surface area is this, okay, the interface area of all the voids, okay, between spaces between the particles is exactly the same as the surface area of the particles, okay, because the surface is between the particles and the fluid. So, the surface area of the fluid flowing through the voids is equal to the surface area of the particles in the column. Okay. So, therefore, void surface area will be equal to the number of particles times the area, surface area of one particle. Okay. What is the number of particles? Okay. The number of particles n is equal to the total volume of the particles. Okay. The total volume of the particles is the total volume times 1 minus epsilon. Volume of the particles times 1 minus epsilon is the I am sorry, the total volume of the bed. Epsilon times V is the volume of the voids. 1 minus epsilon times V is the volume of the particles, because whatever is not occupied by voids has to be occupied by particles. So, V into 1 minus epsilon is the total volume of the particles divided by the volume of one particle, Vp, is equal to the number of particles. Okay, in the column. Okay. So, number of particles is the total volume occupied by the particles divided by the volume of one particle. Okay. Therefore, void surface area is equal to V into 1 minus epsilon, okay, AP by Vp. That is the void surface area, and the void volume is V into epsilon. Okay. So, this is the void surface area, this is the void volume. Therefore, the void equivalent diameter, okay, is equal to 6 times the void volume, which is V epsilon, by the void surface area, okay, V into 1 minus epsilon AP by Vp. These V's cancel out and I will just get 6 epsilon Vp by 1 minus epsilon into AP. Okay, that is the equivalent diameter of the voids. Okay. And we know that this combination 6 Vp by AP is the equivalent diameter of the particle. Okay. 6 Vp by AP is the equivalent diameter of the particle. So, this is just equal to, okay, epsilon into equivalent diameter of the particle. I have written this without the superscript void to say that this is the equivalent diameter of the particle by 1 minus epsilon. Okay. So, I have related the void equivalent diameter to the particle equivalent diameter. Okay. V void is equal to the superficial velocity divided by epsilon. Okay. Superficial velocity is the flow rate divided by the cross sectional area without the particles. Okay. That divided by epsilon is the velocity through the voids. Okay. So, these are the relevant length and velocity scale for the voids. Okay. And once you have this relevant length and velocity scale for the voids, you can define what are the parameters, the friction factor and the Reynolds number. Okay. The Reynolds number is equal to rho v void equivalent diameter void by mu. Okay. Is equal to rho into Vs by epsilon into Vs divided by epsilon into epsilon dE by 1 minus epsilon. Okay. So, this is the Reynolds number based upon the equivalent diameter of the particle and the superficial velocity. Okay. So, this is the Reynolds number based upon the equivalent diameter of the particle and the superficial velocity. What about the friction factor? Okay. Recall that the friction factor relates the pressure difference required to drive the flow. Okay. Relates the pressure difference per unit length that is required to drive the flow, defined the same way as it was for the previously for the pipe flow. Okay. With an important difference. Okay. So, in this case the friction factor is usually defined as minus delta P by L, okay, because the inlet pressure has to be higher than the outlet pressure. So, delta P is negative, okay, and it is defined as 1 over rho V void by I am sorry V void the whole square divided by the equivalent diameter of the void. Okay. If you recall, for the fanning friction factor we had a factor of 2 in the denominator here, okay, for the flow through a pipe, and the Darcy friction factor it was a half. Okay. In this case, by convention for a packed column there is no factor of 2 in the denominator. Okay. So, that is just a convention in contrast to what is usually done for a pipe flow. Okay. The friction factor is minus delta P by L into 1 by rho V void square by equivalent diameter of the void. Okay. So, that is the friction factor. Okay. So, I can write this as minus delta P by L into dE void equivalent diameter of the void by rho V void the whole square. Okay. And I substitute these expressions for the equivalent diameter and the velocity, okay, into the expression for the friction factor. So, this minus delta P by L. Okay. Diameter of the void is epsilon dE by 1 minus epsilon, okay, and then 1 over rho into Vs by epsilon the whole square, okay, because the velocity through the void is velocity superficial velocity divided by epsilon. Okay. And if I put all this together, I will get minus delta P by L into epsilon cubed dE by rho Vs square into 1 minus epsilon. Okay. So, these are the friction factor and the Reynolds number expressions for the flow through a packed column, expressed in terms of the equivalent diameter of the particle, the superficial velocity and the void fraction. Okay. And the correlation that is used between the friction factor and the Reynolds number is of the form, okay, 150 by Re plus 1.75. Okay. This is called the Ergun correlation. It is called the Ergun correlation, that relates the friction factor and the Reynolds number for the flow through a packed column. In the limit of Reynolds number becoming small, you would expect the friction factor to be proportional to 1 over the Reynolds number, because the Reynolds number is the ratio of inertial and viscous effects. If the Reynolds number is small, inertial effects are not important, density is no longer a parameter, and therefore you can get the friction, the pressure drop scaled by viscous scales has to be a constant, which implies that the friction factor is proportional to 1 over Reynolds number. For a packed column, that coefficient is 150. Okay. In the limit of high Reynolds numbers, you would expect the friction factor to be independent of Reynolds number, because at high Reynolds numbers it is dominated by inertia and viscosity is not important. And this friction factor correlation is uniformly applicable in both the limits, okay, for predicting the pressure drop in a packed column. Okay. So I've given you how do you define the void fraction and the superficial velocity. Okay. The equivalent diameter of the voids, because the fluid is actually flowing through the voids. So you have to define the equivalent diameter for the voids, and the velocity through the voids in terms of the superficial velocity. Okay. So the equivalent diameter in terms of the particle equivalent diameter, and the velocity through the voids in terms of the superficial velocity. Okay. And once you have that, you can define the Reynolds number and the friction factor, and the Ergun correlation can be used to calculate the relation between the friction factor and the Reynolds number. Okay. So let us use this to solve a problem. Okay. Problem is as follows: water of density 10 power 3. Water density is usually 1000 kilograms per meter cubed. And viscosity 10 power minus 3 kg per meter per second, okay, is pumped upwards through a column of spherical particles of diameter 1 centimeter and density 1.2 into 10 power 3. kg per meter cubed. Okay. And void fraction 0.4. Estimate the velocity beyond which the particles are fluidized. Okay. And what is the Reynolds number? So, how do we solve this? To give you some context, you have a bed of particles of a certain length, okay, this is the length. They are applying a pressure difference across, okay, across the ends, okay, in order for the fluid to flow through. And as the fluid is flowing through, it is exerting an upward force on the particles, okay. It is exerting a net upward force on the particles. When that upward force becomes greater than the downward gravitational force minus the buoyancy force, the particles will spontaneously start to move upwards, okay. As long as the force on the bed is smaller than the difference between the gravitational and the buoyancy forces, the particle will rest at the bottom, because there is a net force that is being exerted on the bottom. Once the pressure difference, the net force on the bed due to the pressure difference exceeds the difference between the gravitational and the buoyancy force, the particles will start to move upwards, okay. So, what is the total gravitational minus buoyancy force? Okay. This is going to be equal to rho particle minus the rho fluid, okay, because the net force is proportional to the difference in density between the particle and the fluid, okay. So, that is going to be equal to the difference in the force the density between the particle and the fluid. This is the mass densities, okay. I have to multiply that by the total volume to get the total mass, okay. The total volume of the bed is A times L, okay, the cross sectional area times L, that is the total volume of the entire bed, area times the length. The fraction of that which is void is epsilon. That means that the fraction of that which is particles is 1 minus epsilon, okay. This is the total mass of all the particles in the bed multiplied by the gravitational acceleration, gives you the difference between the downward gravitational force on the particles minus the buoyancy force, because these particles are in liquid water. That is the net force, okay, downward force. The net upward force is going to be equal to just the pressure difference into the total area, okay. Pressure difference, pressure is force per unit area, pressure difference times the cross sectional area is the total upward force. When these two are equal, then the downward force, gravitational minus buoyancy, is equal to the net force upward due to the pressure difference between the bottom and the top, okay. And you can see that the areas cancel out, okay, and I will get minus delta P by L is equal to 1 minus epsilon delta rho G. Okay. And I can express this delta P by L in terms of the friction factor, okay. I can express delta P by L in terms of the friction factor, okay. I substitute here for delta P by L in terms of the friction factor. So, this is equal to rho Vs square into 1 minus epsilon by epsilon cubed dP, okay, is equal to 1 minus epsilon, okay. I have to multiply by the friction factor as well, okay. The friction factor as well is equal to 1 minus epsilon. Okay. So, note that minus delta P by L is equal to the friction factor into rho Vs square 1 minus epsilon by epsilon cubed dE. Okay. So, I just substitute the friction factor there. This is equal to 1 minus epsilon delta rho times G, where delta rho is the difference in density between the particles and the fluid. And for the friction factor, I substitute F is equal to 150 by Re plus 1.75. Okay. It's equal to 150 mu into 1 minus epsilon by rho V superficial times d. Okay. Note that Reynolds number was equal to rho Vs d by mu into 1 minus epsilon, okay, plus 1.75. Okay. So, for the therefore, I have the friction factor 150 mu into 1 minus epsilon by rho Vs d plus 1.75, okay, into rho Vs square into 1 minus epsilon by epsilon cubed dp. Okay. That is, this friction factor, I have used this correlation, and this second term here, okay, is equal to 1 minus epsilon delta rho g. Now, I have to just substitute numerical values. Okay. Rho is equal to 10 power 3 kg per meter cubed, mu is equal to 10 power minus 3 kg per meter per second, and epsilon is equal to 0.4. Okay, void fraction was 0.4, and delta rho, particles had density 1200. Okay, particles had density 1200. Particles at density 1200, 1.2, and fluid was 1000. So, the difference is 200 kg per meter cubed, okay, and g is equal to 10 meters per second square. Okay. So, to just substitute all of these values into this quadratic equation, okay, and to substitute all of these values into this quadratic equation. Note that this is a quadratic equation because I have a Vs square here and I have a 1 over Vs here, okay, plus a constant. So, I get a quadratic equation for Vs. Okay. Substitute this and solve the quadratic equation to find out what is the superficial velocity, which in this case turns out to be 0.026 meters per second. 2.5 centimeters per second is what you would require to fluidize the particles, okay, in this particular case. Okay. That we got from a combination of a force balance on the packed column and the Ergun equation for the friction factor, okay, for the packed column. Substituted those two to find out at what point the pressure difference times the cross sectional area is equal to the weight of the particles minus the buoyancy force. And the Reynolds number can be calculated is equal to rho Vs dE by okay, I had to substitute here dP is also equal to, how much was it, 1 centimeter, okay, by 1 minus epsilon into mu. Okay. And if you substitute the values, the superficial velocity, the density, the diameter, the void fraction and viscosity, this turns out to be 410. Okay. So, this is an example of where you can use the Ergun correlation and the definition of the friction factor for a packed column to predict at what velocity the packed column will fluidize. Okay. So, this is one of those examples. Okay. So, I have covered flow through a pipe, flow past a flat plate, flow around particles and bubbles, flow through a packed column. Okay. The momentum transfer, the friction factor correlation, the skin friction factor correlation and the drag coefficient in each of these. Okay. In each of these cases, correlations for those in the limit of low and high Reynolds numbers. Okay. And We will complete this section on momentum transfer by looking at mixing equipment, the mixing by an impeller for example, the power number for that, and how do we use that power number to derive correlations. Okay. So, that we will continue in the next lecture. I will see you then.